So here is a question that asks us to find the distance from the Earth's center to a point outside the Earth. And they give us a ratio for the acceleration due to gravity. And it's 1/28 the value at the Earth's surface. Also important to solving this problem is that it's given that the radius of the Earth is 6.38 times 10 to the 3 kilometers. Alright, so here's a little diagram showing that here's the Earth and here's an outside point that we're trying to solve for. So at the Earth, the gravity would be G, and at the outside point, it's 1/28 of G. So the formula for gravitational pull is G equals big G, which is a constant, times m1, mass 1, m2, mass 2, over radius squared, the distance between the objects squared. On the Earth's surface, formula is the same. We just get that G, which is 9.8 meters per second squared, is gravity constant times the mass of the object times the mass of the second object divided by the radius of the Earth. And they tell us at an outside point that the gravity is 1/28 of G. So here is the formula for the outside point. Now the only two things that differ in this formula from the first formula, the only thing that differs in this formula from the first formula is that the radius is different. This is R2, this is R1. R1 is the Earth, R2 is the distance outside. So what you need for this problem is the radius for each. So you can isolate r squared on each expression. And you get r1 squared g, right, just by rewriting it, equals g, big G, the constant, m1, m2. And then for the second formula, for the point outside the Earth, you get 1/28 r squared times g equals g times m1, m2. Now, the g, the m1, and the m2 are all constants in this problem, and they don't change. So you can set the equations equal to each other and cancel out those items that are the same, and what you get left with is r1 squared equals g, r1 squared times g equals 1/28 r2 squared g. And again, it's probably clear now to see that the g's cancel out, so what you're left with is r1 squared equals 1/28 of r2 squared. So what you do is you isolate the r2 squared, because that's the number that we're interested in finding, and you get that r2 squared equals r1 squared times 28. You just multiplied the 28 on both sides of the equation. So r1 is given as 6.38 times 10 to the third kilometers, so you plug this in. And you get r2 squared equals 28 times 6.3 times 10 to the 3 kilometers squared. And then you do the math on that, and you get this mess of a number in kilometers squared. And then you have to square that, because you square the r2, right, to get it down to just regular. And what you get after you square all of this is 33,759.8 kilometers, more or less. And you can rewrite that so it's a little bit cleaner into scientific notation. So R2 equals 3.376 times 10 to the 4th kilometers. Or if you wanted to write that in meters, it would just be 3.38 times 10 to the 7th meters. And this makes intuitive sense, because if it's going to have a gravitational pull of 1/28 of what's g, it's going to be significantly farther from the Earth than the Earth's surface. So if the Earth's surface is here, 6.38 times 10 to the third kilometers, this outside point needs to have a radius that is significantly larger to give it 1/28 the gravitational pull. And that's what we get here with 3.38 times 10 to the 7th meters, right? Or 3.36 times 10 to the 4th kilometers. So that is the answer.